The Sahara Desert is supposed to be the very definition of stillness. 9 million square kilometers of sand, rock, and emptiness stretching across North Africa with almost nothing alive in sight. No rivers flow across its surface. No rain falls for years at a time in some regions. It is the largest hot desert on the planet, and for most of human history, it has represented the closest thing on Earth to a frozen, motionless landscape. But satellites orbiting hundreds of kilometers above the Sahara have picked up something that should not be happening in a place this dry and this still. The ground itself is moving, not earthquakes, not landslides, not sand dunes shifting in the wind, although that does happen too. Something deeper and far stranger. Across vast stretches of the Sahara, the solid bedrock beneath the sand is rising and falling, millimeter by millimeter, in slow, measurable cycles that scientists can now track from space with extraordinary precision. And the explanation for why this is happening connects directly to one of the largest and strangest hidden features of our entire planet, an ocean of ancient water buried so deep and so vast that it makes the deserts above it almost a cruel joke played by nature. To understand how scientists figured this out, you first need to understand the technology that made it possible, because the discovery itself would have been completely impossible just a few decades ago. The method is called interferometric synthetic aperture radar, or InSAR for short. The way it works is genuinely remarkable. A satellite equipped with a radar instrument passes over a specific patch of the Earth's surface and sends a radar signal down toward the ground. That signal bounces off the surface and returns to the satellite, and the satellite precisely measures how long the round trip took. Then, days, weeks, or months later, the same satellite passes over the exact same patch of ground again and repeats the measurement. If the ground has shifted even slightly during that time, moving closer to or farther away from the satellite by even a few millimeters, the radar signal's return time changes in a way that can be measured with extraordinary precision. By comparing thousands or even millions of these measurements across a region, scientists can build detailed maps showing exactly where the ground has risen, where it has sunk, and by how much, all without a single person ever needing to set foot on site. This technology has already been used around the world to monitor land sinking in cities like Mexico City and Jakarta due to excessive groundwater pumping, to track volcanic activity by detecting subtle bulging of the ground before an eruption, and to measure the gradual settling of land after major earthquakes. The European Space Agency's Sentinel-1 satellite constellation, launched starting in 2014, along with similar radar satellites operated by Japan, the United States, and other space agencies, now provides continuous radar coverage of nearly the entire planet, generating the kind of long-term high-resolution dataset that scientists need to detect movements as small as a few millimeters per year across enormous areas. When researchers turned this technology toward the Sahara Desert, what they found connects to a feature that very few people outside of hydrology and geology have ever heard of, despite the fact that it is one of the single largest bodies of fresh water anywhere on Earth. It is called the Nubian Sandstone Aquifer System, and it sits hidden beneath the eastern Sahara, spanning an area of approximately 6 million square kilometers beneath 4 countries: Egypt, Libya, Sudan, and Chad. To put that scale into perspective, the aquifer system underlies an area larger than the entire country of Argentina. It is widely recognized as the largest known fossil water aquifer system on the planet, containing an estimated 150,000 to as much as 450,000 cubic kilometers of fresh groundwater. According to research published by the International Atomic Energy Agency, the total reserves held within this aquifer are roughly equivalent to about 500 years of the Nile River's entire discharge, and the volume is approximately 20 times larger than all of North America's Great Lakes combined. This is an ocean of water, hidden in complete darkness beneath one of the driest and most lifeless landscapes on the surface of the Earth. The water itself tells an extraordinary story about the deep history of this region. Scientists refer to it as fossil water or paleo water because virtually none of it is being replenished today. The Sahara, as we know it, the endless dunes, the cracked earth, the brutal heat, is a relatively recent climatic phase in the long history of this landscape. Geological and paleoclimate research has established that the Sahara has cycled repeatedly between extremely dry periods and dramatically wetter, greener periods over hundreds of thousands of years, driven by long-term shifts in Earth's orbital patterns known as Milankovitch cycles. During these wetter phases, called African humid periods by climate scientists, what is now the Sahara was covered in lakes, rivers, grasslands, and savanna ecosystems, supporting elephants, hippos, crocodiles, and early human populations, evidence for all of which has been found in fossils, ancient rock art, and dried lake bed sediments across the region. Rain falling across that ancient green landscape soaked into the sandstone rock layers below, and over tens of thousands of years, it accumulated into the vast underground reservoir we now call the Nubian Sandstone Aquifer System. Then, as Earth's orbital cycles shifted again, the rain stopped, the vegetation died, and the region slowly transformed into the desert that exists today. But the water that had already soaked deep underground remained trapped there, sealed beneath layers of rock, locked away from the increasingly hostile climate above. Radiocarbon dating of water samples drawn from various points across the aquifer indicates that this water was recharged during multiple wet periods stretching back as far as 1 million years, though scientists generally consider the most significant and recent recharge events to have occurred within roughly the last 30,000 years. So what does any of this ancient hidden water have to do with the ground itself moving? This is where the InSAR satellite data becomes genuinely fascinating, because researchers studying ground deformation across arid regions worldwide, including parts of the Sahara and similar desert aquifer systems, have established a clear and consistent physical relationship. When water is extracted from an underground aquifer faster than it naturally drains or shifts, the ground above that aquifer subsides, sinking downward as the rock and sediment layers compact into the space the water used to occupy. Conversely, when water levels within an aquifer rise, whether from natural underground flow, seasonal pressure changes, or recharge, the ground above can actually lift upward, even if only by a few millimeters. This phenomenon has been documented and measured with InSAR technology in aquifer systems on every populated continent. Researchers using Sentinel-1 satellite data have measured measurable land subsidence in California's Central Valley, correlating directly with groundwater pumping cycles, similar patterns in Mexico City, where subsidence has reached extreme levels due to decades of unsustainable groundwater extraction. In Lahore, Pakistan, where PES InSAR studies have mapped subsidence zones tied directly to falling water tables, and in numerous river valleys and agricultural basins across Iran, Turkey, and China. The underlying physics is consistent everywhere it has been studied. The ground is not a rigid, unchanging surface. It behaves, in a very real and measurable sense, like a slowly breathing structure, responding to the rise and fall of the water reservoirs hidden far beneath it. Across the Sahara, specifically, scientific teams have applied this same radar interferometry approach to study how the surface above the Nubian Sandstone Aquifer System and other major Saharan aquifer systems, including the Northwestern Sahara Aquifer System, responds to groundwater dynamics. Research published through international hydrological surveys examining space-based observation of groundwater across Africa has confirmed that satellite radar interferometry can successfully detect ground deformation patterns linked to aquifer storage changes, even across the extremely arid and largely unpopulated stretches of the Sahara, where traditional ground-based monitoring equipment is sparse, expensive to maintain, and difficult to access. In regions where groundwater extraction has intensified, such as around Libya's Great Man-Made River Project, one of the largest water transport infrastructure projects ever constructed, which draws an estimated 4 cubic kilometers of water annually from the Nubian Aquifer to supply cities and agricultural zones along Libya's coast, scientists have specifically used InSAR data to monitor whether the intensive, sustained extraction is causing measurable subsidence at the surface above the extraction zones. This matters enormously for practical reasons beyond pure scientific curiosity. If the ground above a heavily pumped section of the aquifer subsides too much or too unevenly, it can damage the very infrastructure built to extract and transport that water in the first place, including the thousands of kilometers of massive underground pipelines that make up the Great Man-Made River System. There is also a deeper geological dimension to why parts of the Sahara show this kind of subtle ground movement beyond just groundwater extraction by humans. The Sahara sits across a continental region with a long and complex geological history, including ancient fault systems, sedimentary basins, and areas of ongoing, extremely slow tectonic adjustment. Research into groundwater-related processes shaping Saharan landscapes has shown that groundwater itself plays an active role in shaping surface features across the desert over geological timescales, including theater-headed valleys, depressions, escarpments, and ancient lakebed formations called playas. In some areas, groundwater from deep aquifers like the Nubian system rises along these ancient fault lines, interacting with shallower water layers and subtly influencing surface conditions in ways that radar satellites can now detect and measure with a level of precision that would have been the stuff of science fiction even 30 years ago. What makes this entire area of research so significant is not simply the technical achievement of measuring millimeter-scale ground movement from orbit, impressive as that is, it is what this movement reveals about the relationship between the visible world we can see and the invisible world hidden beneath it. The Sahara looks, from the ground and from ordinary satellite photography, like the most static, unchanging landscape imaginable. Vast, motionless, eternal. But radar interferometry reveals a completely different reality underneath that stillness. There's a colossal reservoir of ancient water down there, slowly shifting, slowly draining in places where humans have drilled into it, and the surface above responds to every change, rising and falling in tiny increments that no human eye could ever perceive directly, but that a satellite passing overhead can measure with millimeter precision. The ground is not the immovable foundation we instinctively assume it to be. It is closely, continuously connected to whatever lies beneath it, breathing in step with the rise and fall of unseen water reservoirs that took hundreds of thousands of years to form and that, once depleted, may never refill again on any timescale that matters to human civilization. This research carries serious practical weight for the millions of people living across North Africa who depend, directly or indirectly, on water drawn from beneath the Sahara. Because the Nubian Sandstone Aquifer System and similar Saharan aquifer systems receive essentially no meaningful natural recharge, under today's hyper-arid climate conditions, every cubic kilometer of water extracted for agriculture, drinking water, and urban development in Egypt, Libya, Sudan, and Chad is, for all practical purposes, a withdrawal from a finite, non-renewable savings account that was filled by rains that fell tens of thousands of years ago. Monitoring the ground deformation patterns above these aquifers using satellite radar gives scientists and water resource planners an unprecedented, continuous, and remarkably precise tool for tracking how quickly that ancient water is actually being depleted, where the depletion is most severe, and where the ground itself may eventually become unstable as a direct consequence. It transforms a question that used to require expensive, sparse, and difficult-to-maintain ground sensors scattered across an enormous and largely inaccessible desert into a problem that can be monitored continuously and comprehensively from a satellite, orbiting peacefully hundreds of kilometers above the Earth. The next time you see an image of the Sahara Desert, that endless expanse of dunes stretching to the horizon under a punishing sun, it is worth remembering that what looks like the most still, dead landscape on the planet is anything but truly motionless. Underneath that sand and rock lies an ocean's worth of ancient water, the rainfall of a world that existed long before the desert ever formed. And the ground above it is rising and falling in response, breathing in millimeters, in cycles that stretch across years and decades, visible only to instruments built to detect what no human eye ever could. The Sahara is not simply old. It is alive in a sense, not biologically, but geologically and hydrologically, locked in a slow, continuous conversation between the surface we walk on and the deep, ancient water hidden far below it, a conversation that satellites have only just learned how to listen to.